Last time we discussed the limit. What is a limit? What's the formula for a limit? Not equals f, but close. So it's the limit as x approaches c, very good, of the function. What does that equal? C is in here. F is right there.
So we can say this.
It's the limit. Yeah, which is, you can say that if it exists, then f of c equals L. Why is it if it exists? This is what we talked about last time. Why is it if it exists? What's that? Well, if there's discontinuity, remember the example we had last time. Was something like this. So what's the limit when x equals -1? Remember what we did last time? Nope. Because we're looking for limits here. Did anybody bother looking at their notes last time? I'm gonna start having quizzes in the morning. And everybody online, I'm gonna send them messages. We're gonna have a quiz every morning over the previous day's lecture. Because when you guys come in here, all you do is look at your cell phones and your computers and waste yours and my time. Because when we talked about limit, we talked about it doesn't have to exist to be there. It simply has to approach the value. So what is this graph going to look like? Because if you can draw the graph, it'll help you understand what's going on. So what is this graph of this function going to look like?
-1 plus 2 divided by -1.
What are you doing? Ask for the graph.
Yeah.
It's a rational expression. So from algebra, we talked about asymptotes. So what's the vertical asymptote of this equation? What's the vertical asymptote of this equation? What is a vertical asymptote? What's an asymptote? Let's just start with the basics. What's an asymptote? It doesn't have to be an x, but it could be, we also have horizontal asymptotes. That's a y point. Correct. Okay, it is a vertical line, yes, from top to bottom, but where is it situated and what does it mean? Not necessarily true. Because we have two types of asymptotes. The vertical asymptote does only exist when you have rational equations. What can you not have in a rational equation? A fraction. Let me see. This is called a rational. It's a fraction. What can you not have in a fraction? What's that? What can you not have in a fraction? What is illegal in a fraction? Very good. You cannot have a zero on the bottom. That is your vertical asymptote. The x values that make your denominator equal to zero. Basically, where it makes your function undefined. So our vertical asymptote is where in this question? Put your phone away. You don't need your phone.
Remember asymptote, what is mean?
I know. I want you guys to memorize it, not look it up. Because if I want you guys to look it up, then I don't need to be here anymore. You guys don't need your phones or computers on the tables. Like I told my other classes, it is possible to survive 1 hour without being on your telephone. I've seen it done. Students do survive 1 hour without being on a phone. You don't have to be on your phone all the time. So what's our vertical asymptote here? We just gave you the definition. So what's our vertical asymptote? Very good. Take your bottom, set it equal to 0. So what is x going to equal? So -1 is my vertical asymptote. That's my vertical asymptote. The graph cannot cross that line because it makes the function undefined. Do we have a horizontal asymptote? Okay, if so, where?
You said that you cannot be on a zero, right? Only on
You cannot have 0 on the bottom. That's a vertical asymptote. What is a horizontal asymptote?
uh, have to be based on
In our example, our horizontal asymptote is 1, or the equation y equals 1. Now, why is that? Because remember, if you're going to be engineers, you have to know the rules of algebra and trigonometry. Those are the basics of calculus and everything above here: differential equations, linear algebra, complex analysis, everything. Algebra is the basis. How do you find the horizontal asymptote? It all depends these are polynomials, but the leading terms are the most important part. The leading terms In other words, it's the term of a polynomial with the largest exponent. That's the leading term. The leading term. Because the leading term, it has the largest exponent, so it controls most what happens to that function. We have, depending on the degrees of your polynomials, the exponents, one of three things can happen. If the top exponent is bigger than the bottom exponent, then you don't have a horizontal asymptote. Why? Why is there no horizontal asymptote if the top is bigger than the bottom? If the top is bigger than the bottom, I can simplify it by subtracting the exponents. What happens when x goes to infinity? Where does this value go when x goes to infinity? What's infinity squared? Infinity times infinity is what? Yes, so this one goes to infinity. That's why there's no horizontal asymptote. If there's more x's on top than the bottom, then it goes on to infinity. That's the first condition. If the exponents are equal, of our leading terms. If our exponents are equal in our leading terms, what happens there?
If they were equal, that means
Equals A over B, because the variables cancel. Very good. If the top is smaller than the bottom, always subtract the larger minus smaller. If you have more on the bottom, where does that go when x goes to infinity? What's that? What did you say? As x goes to infinity, what happens here?
it's not the same one.
No, let me get on the line. No, on the line because the number is so small.
And it goes to where? If it's so small, yes. Very good. 1/1 is 1. 1/2 is a half. 1/10 is 1/10. 1/100 is 1/100th. So the bigger the bottom number, the smaller the number, so it goes to 0. So in our example, what's our horizontal asymptote? Why'd you get a 1? Don't just copy what I said. I don't need parrots. I don't need recordings. I need people to answer questions. Why? What is the horizontal asymptote of my function? To find the horizontal asymptote, what do you have to look at? The leading terms. What are the leading terms? What's the leading term on top? X. What's the leading term on the bottom? X divided by X is what? 1. Since the exponents are equal, it's simply the coefficients. 1 divided by 1 is 1. That's a horizontal asymptote. So we know our graph has to look something like that. Do we have any intercepts? Do we have any x-intercepts or y-intercepts? How do you find the x-intercepts and y-intercepts?
White.
Okay, what do you do with the x-intercept?
White.
Yes. First step, set y equal to 0. So in our equation, and then you solve for x. So we have 0 equals x plus 2, x plus 1. Multiply both sides by x plus 1. Again, the only way a fraction can equal 0 is if the top is equal to 0. So x is equal to -2. That's my x-intercept. What's my y-intercept? Well, in this one, set x equal to 0. And then solve for y. So we have y is equal to x plus 2 over x plus 1. What does that give us? Yeah, because the x's disappear. So we have 2 over 1, which is 2. It's always the constant. Y-intercept is always the constant. So the y-intercept is 2. Because there are no other intercepts, we know that our graph will look something like this. That's our graph. And here's something from algebra your teacher probably never told you, or you probably forgot. As your function approaches the vertical asymptote, where does your function go? As your function approaches the vertical asymptote, or as our graph approaches the vertical asymptote, this vertical line here, where is the graph going? Look at the picture, look at the graph. Nope. Look at the graph. Where are the arrows taking you? Or look at the other side. Yes, it's either going to infinity or negative infinity. That's how you know it's a vertical asymptote. As the function gets closer to the vertical asymptote, your graph will go either to positive or negative infinity. As it approaches the horizontal asymptote, it's approaching that horizontal or 0, that horizontal asymptote. That's how you can tell asymptotes. All right. Let's look at example 1. Consider the function y equals 2x minus 1 near the value at x equals 4. Notice it says near, not at. Because whenever you talk about something getting near, you're talking about what is the limit? What value is it approaching? Not getting to, but is it approaching? So what we would do here, we'd have this. We'd have the limit as x approaches, gets near to 4 of our function 2x minus 1. What does that equal? So, very good, very good. 2 times 4 is 8. 8 minus 1 is 7. So my limit is 7. It's approaching that value. So that's whenever we say something getting near or it's approaching it, then that's what we're saying. We're saying that our value as x approaches 4, the function is approaching the value of 7. Yeah, if it works, if you could just take your c value and plug it straight inside there, if it exists, that's always going to be true if it exists. Now, what does that really tell us? What this thing tells us, since this is our limit point, we can look at the function x minus 7, the absolute value of it, because we only want the positive side. That's the same as our function 2x minus 1 minus 7 is equal to what? If I complete this, what do I get? I could drop the parentheses. Then I have 2x minus 8. Well, we're looking at, remember, now, pictorially, last time I gave you this picture. Let's use even a linear equation. What this one represents is the limit of the function f of x as x approaches c is equal to L. That's what this represents. You notice, as it says, as x approaches c, doesn't say x equals c, it says as it approaches c. So as our values get closer and closer and closer to c, our y values, our answers, are getting closer and closer and closer to L. Again, as our x values get closer to c from both directions, our y values are getting closer and closer and closer to L. That's what the whole limit thing is all about. That's what we're looking at. Now, what we're looking now, we have to introduce ranges. In our horizontal aspect, we'll call those the delta values. And our vertical ones, we'll call those the epsilon. Epsilon and delta are infinitely small numbers. So in other words, what we're saying here is this side here is C plus delta, and this is C minus delta. The smaller delta becomes, it gets closer, closer, closer to C. It does the same thing over here. This is L minus epsilon. This is L plus epsilon. That's what we're going to look at in this section. So let's define a limit. The definition of a limit. Because we have to have, we know what it looks like. It looks like this. So we have to first start with this one. Let f of x be defined on an open interval. Containing C. But not necessarily at C. So you have an open interval, A and B. Inside there, there's a value C. But the function's got to be continuous inside that open interval. So let f of x be defined on an open interval A, B, containing C, but not necessarily at C. The limit of our function f of x as x approaches C is some number L. Okay, we've been using this already. That's nothing new. But now, since we've introduced epsilon and deltas, we have to get infinitely close to C. As we get infinitely close to C, we get infinitely close to L. So now, if for every epsilon greater than 0, there exists a corresponding number delta, which is also greater than 0, such that now we come to the epsilon delta proof. For every epsilon greater than 0, remember, where does epsilon exist? On the x or the y-axis? On the y-axis. It's the vertical. What we're saying here is this. Remember our picture. This is L. This is C. And we have some interval. This is our function f of x. So what this is saying is the difference between our function and our limit has got to be less than some epsilon, some infinitely small epsilon. This is true whenever, remember, it has to be greater than 0, we get some value C, or that's on our x-axis, that the difference of which is going to be less than some value delta. Think about this, what it means. What is x minus c? What does x minus c represent? Or c is here. This is the x-axis. So for any value x, x minus c is the distance between there. So basically what we're saying is x minus c at worst case is equal to delta. But we don't want it equal to delta, we want it to be smaller because it's an open interval. It cannot equal delta because we're dealing with an open interval AB. You cannot equal the endpoints. A and B is not fixed. If it works when it's 4 pieces away, it can work when it's 2 pieces away. Or it can work when it's 1 piece away, or half a piece, or an eighth, or a tenth, or a hundredth, or a millionth. So this is how we prove the limit exists. Let's look for an example. Well, these pictures are better than my drawings. So here's our function f of x, and there's our c, and there's our L. The first part of our proof, of our definition, is f of x minus L is less than some epsilon. So we have, our epsilon is 1 over, this is our limit. So our epsilon is the distance between there. That's less than some epsilon. So this is true whenever the distance we have from our value x minus delta from this interval, as delta gets smaller and smaller and smaller, we get closer. Our x minus delta becomes c. Okay, now the first one, notice how wide it was? It was at 1/10. Now we shrunk it even further. Our epsilon is no longer 1 over 10. Our epsilon now is 1 over 100. It's getting closer and closer. So what does that mean? Since our epsilon got smaller, so does our delta. Our c minus delta and c plus delta, it's getting smaller and smaller and smaller. Now we go over 1 over 1,000. Our epsilon is now 1 over 1,000. It's getting smaller. The distance from wherever our answers could be to our L, it's getting smaller, which means our horizontal distance has to be getting smaller and smaller and smaller. So that's what we're doing. So we can keep on changing the epsilon value. When we change the epsilon value, we have just now have to change our c plus and c minus delta. Our delta value has to get smaller, has to get closer and closer and closer, so that c equals c. So we're looking at, basically what we're saying is, as epsilon goes to 0, the distance from the limit to the value, as it goes to 0, the distance from our value goes from our c value to our boundaries, it goes to 0. It gets infinitely small. Never equals, but it gets infinitely small. That's why your limit doesn't have to exist to exist. It simply has to approach it from both directions. So show this exists. Let's look at this one. example 2. The limit as x approaches 1 of 5x minus 3 is equal to 2. We're asked to prove that. We have to show this. So the way we should, okay, now, is this a true value? How do we get that? Take 1. 5 times 1 is 5, minus 3 is 2. Yes, that's true. But we have to show that it's true. To do that, we have to use the f of x minus L is less than epsilon when x minus c is less than some delta. That's what we have to do. So let's plug in. What is f of x?
That's, one.
What is f of x? Look at the definition of a limit formula. Look at it again. What is it? F of x is y, yes. But what is my f of x? What do I put here for f of x? 5x minus 3. This is my f of x. Look at the definition. Look at the examples we've always been writing. So it's 5x minus 3 minus, what's my limit? What's my L? 2 is less than some epsilon. When, what is C? Is less than some delta. So all we did was plug in everything in there. And basically what we're trying to do is we're going to try to make this equal this. We're going to try to make this inside this absolute value equal that. Because once we can do that, then we can say that epsilon and delta are equal, are related somehow. So let's fix this one. So we have 5x minus 3 minus 2 is less than epsilon when 0 is less than x minus 1 is less than delta. 5x minus 5 is less than epsilon. Yeah, and those of you online, it's much easier if you go ahead and just speak through your microphone, because I rarely ever look at the message button. All right. What can we do inside here? Can we do anything algebraically? Is there anything come? Remember, we want this number to try to look like this. We can factor out a 5, which will leave us with an x minus 1. For the rules of exponents, I can now take these absolute value of 5, absolute value of x minus 1 is less than epsilon. The absolute value of 5 is 5. Remember, we want to try to get this to look like this. What do we have to get rid of on this side? What do we have to get rid of? Let's get rid of the 5. So we divide both sides by 5. So our absolute value of x minus 1 is less than epsilon over 5. Less than delta. So now we can look at how are epsilon and delta related. Remember, both epsilon and delta are both positive numbers. They both have to be greater than 0. Delta is right here, but epsilon is, that's part of the definition. So epsilon is greater than 0. So is delta. So how are delta and epsilon related? But look at it. Are these the same? So if these are the same, if these are equal, what do you think about these two? They have to be equal. So what this thing tells us is epsilon divided by 5 is equal to delta. That's the relationship. So however close, remember, delta is how far x is, or c is from our x values. As that gets smaller, this one gets smaller even faster. So therefore, the limit exists. And that proves it. That tells us a relationship. Typically, what's going to happen, I'll say, I'll give you an epsilon. Something like that. But remember, it's infinitely close. If epsilon equals 0.001, what is delta? So it's going to be 0.0002. If this is how close the y values are to L, this is how close the x values are to C. A lot closer. So as this gets closer, this gets closer. That's how we tell, that's how you determine if it exists. Example 3A. Prove that the limit as x approaches C of x is equal to, what is it equal? If we have this, it's called the identity function. The limit of x as x approaches C, what does that equal? C. Prove that. We have to prove it using the epsilon delta. And then we're also going to prove the other formula we learned is on a constant function. As x approaches C of some constant function, it equals that constant value. So let's prove this one first. How do we prove it? Whenever it says proof, you have to use the epsilon delta. What's the formula for the epsilon delta? Very good. Why is it f of x and L? It's not a trick question. Where is f of x? Vertical or horizontal? It's the vertical. It's the y value. What is L? That's the value on the vertical axis. So these two go together. It's less than what? Epsilon. When what is true? Well, we have to know that our delta has to be greater than 0. And delta gives the horizontal. So it's the distance between X and C. So plug in your values. What is f of x? It's x minus L. What's my L value? C is less than epsilon when absolute value of x minus C is less than delta. So what does that tell us? How are epsilon and delta related? Epsilon equals delta. So however infinitely close delta becomes, so are epsilon, so it's always going to be true. Now let's do our constant function. So we have f of x minus L is less than epsilon when 0 x minus C is less than delta. What's my function? Okay. What's my limit? Is less than epsilon. X minus C is less than delta. So what is K minus K? So 0 is less than epsilon when this is true. So what does this tell us? Remember, epsilon has to be greater than 0, always. So what this says, it's true for everything. I'm sorry, we were supposed to do here. Yeah, see. So this is always true. It's going to be the same value because it never changes. So 0 is equal to delta. And the way that is, it never changes. X and C are going to be the same, the distance. Now we're going to look at something that is not symmetric. About C. What does that mean? Typically, when we talk about symmetry in our, if this is our value C, typically we have C minus delta and C plus delta. So it's equal distance. That's typically how we do it. But now we can have C minus delta plus 1, C plus delta plus 3. They don't have to be symmetric anymore. If this happens, if we get to a point where our x values are not symmetric, in other words, this side and this side are not equal in width, always take which one, larger or smaller? Always take the smaller, because the smaller you pick it, the closer it is to C. So if they're not equal, choose the smaller of the two. And this will make more sense when we do the example. Example 4. Okay, it says. For the limit as x approaches 5 of the square root of x minus 1 equals 2, find a delta greater than 0 that works for epsilon equal 1. So how are you going to start about this? How are you going to do this one? Where do you think you're going to start? Define the limit, okay.
Can you start with, 5 minus 1 on them? 5 minus 1 square root.
If you do that, all we're doing is finding if this is true. That's not going to help us any. So we know that's a true statement already. So how are you going to start this? What are you going to put in there? Do we have any formulas we can use so far? Whenever you're asked to show or prove something, start off with this. So let's fill in our blanks. What do we get? What is f of x? Square root of x minus 1. What's L? 2. And what's our epsilon?
1.
1. It's defined there. So now, since it gave us that, we have to work on this algebraically. In other words, we have to solve for x. How do we do that? When we drop to the absolute value, what do we do with this equation? From algebra. If you have an absolute value less than some value, and you drop the absolute values, then you know it's that this value has to be bigger than the negative of that value, and it has to be less than the positive of that value. It has to be between there, because it's less than. Absolute value is the distance from 0 to a number. So we drop the absolute value here, what do we get? Negative 1 is less than square root of x minus 1 minus 2 is less than 1. I drop the absolute value. Then what?
One minus 7 plus minus 1 plus minus
We're
1.
solving for x.
So,
We have to get rid of the 2. Add 2. This is what's called a tripartite equation. 3 parts. 2 minus 1 is 1. We got square root of x minus 1. Because the 2's cancel. 1 plus 2 is 3. We're trying to get to x. What do we have to do next? Square everybody. We get 1 is less than x minus 1 is less than 9. And then we add 1 to every term. Two is less than x is less than 10. Now, what does that tell us? Where are we going with this right now? What's that helping us with? Because we know that this is true whenever x minus 5 is less than delta. But our interval that we have what's our value C? So we're going from 2 to 10. So since this one exists, only 3, this one's 5, so we take the distance of only 3, and so it's always going to work. It's going to be true for any value epsilon and delta we put in there. What's the next one? Yeah, so as long as x does not equal to 5, we're good to go. Because if x equals 5, then the distance is 0, and that's outside of range. So, but it's going to be true for everything because our 5 is between 2 and 10. What else going to say? Find the limit. Then, okay, we found the limit. Now we're going to find the delta. Part 2 says, or part B, find the delta greater than 0 that works for epsilon equals 1. That is, find delta greater than 0 such that all this stuff is true. So what we have to do is find a delta where this is true. And we know that from this side, our value, I will do that. Our domain, the range of our numbers has to be in the interval 2, 10. Because we just saw this, we have this one here. Right, as long as, right, doesn't equal 5. But because 5 is our C value. We want to get infinitely close to that 5. Yeah. So as we said earlier, our C value is 5. And our range is from 2 to 10. So this side is 3 units, this side is 5 units. So we're going to choose what? So our delta will equal to 3. Because why is this our delta equals 3? Because it deals with the x values. X values with delta, y values with epsilon. So what we have here is this. Because of this, we know that our equation from up here, x minus 1 minus 2 is less than 1 when 0 is less than x minus 5 is less than our delta, which is 3. So that's a pretty big spread. It's a very big spread, actually. So let's look at the graph of this. Our C value is 5. We're going from 2 to 8 to 10. Remember, originally we were going from 2 to 10. So in this domain, we know that we have our limit value, which is 2. So on our vertical one, our limit value is 2, and our epsilon is 1. So I go up 1 and down 1, which as these get closer, so since we're using 3 only, we even get our numbers even smaller. So we could look at inside this range. So as these values get closer to C, what's going to happen to over here? It's going to get closer and closer and closer. So think of this. This is 5. If we cut this in half, let's make that at 4. And this is at 6. If I make it that much smaller, I've decreased that domain to be between these two numbers now. As these get closer, the y's get closer. So it shows us that it's a true statement, it works, and this is our answer. Let's look at another example. Any questions? Look how we solve this one. The difference between this one and the other ones we did, it gave us an epsilon. Once it gives us an epsilon, we have to find the delta value. So we're given an epsilon. We know our y, our f of x, and our limit. Plug those in there, solve for x. This tells us now the domain in which our delta is going to fit into. Because here's our C, and it's minus delta plus delta. And since we solve these, this is 2 and 5, we chose our delta to be 3 units. So it goes 3 units to the left, 3 units to the right. So now we're saying that as long as our delta is greater than 0 and our epsilon equals to 1, our answers will get closer and closer, closer. It'll work. Let's look at example 5. Prove that the limit as x approaches 2 of f of x equals 4. If our function is piecewise defined, it's x squared whenever x does not equal 2, and it's 1 whenever x equals 2. So what are we asked to prove? When we asked to prove this, what formula do we have to use? To prove, we use the f of x minus L is less than epsilon whenever 0 is x minus c is less than delta. So let's plug in everything in there. The only thing is, since we have a piecewise defined function, we don't know exactly what f of x is just yet. Because it varies whether it's equal to or not equal to 2. What is our L? 4. Is less than epsilon whenever 0 x minus c, c is 2, is less than delta. You have a question? So let's see where do we start off with this one? Because we have 2 parts to look at. Those 2. Okay, so first off, we're going to look at this one. First one we'll look at when x does not equal 2. So what do we know? Whenever x is not equal to 2, it's x squared minus 4 is less than epsilon. When this is true. So what do we do first here? How do we fix this? Remember, we have to get this to look like this. Well, first off, yeah, we will factor it. But first we have to get rid of the absolute values. So we have negative epsilon x squared minus 4 is less than epsilon. Add 4 to both sides. So it's negative epsilon plus 4 plus 4 plus 4. So less than x squared. And then square root everybody because we have to get rid of that. So we have negative epsilon plus 4 is less than x is less than epsilon plus 4. Now if we, so what is our epsilon going to be? So this is when that's true. So we know that our function f of x minus 4 is less than epsilon will be true when x does not equal to 2 on this interval. Okay, now what the second part we're looking at? When x equals 2. We follow the same thing there when x equals 2. Because when x equals 2, what happens? X squared minus 4 is 0. 2 minus 2 is 0. So it's true. It's going to be uniform from there on out. Yeah, so for the second part, it's true because if you put 2 inside there, then it's 0 is less than epsilon and 0 is less than delta. Example 6. Given the limit as x approaches c of f of x is equal to some value L, and the limit as x approaches c of g of x equals m, prove the limit as x approaches c of f of x plus g of x equals L plus m. Have we seen that before anywhere? Where? Last class in the rules of limits. This is the sum rule. So let's prove this. And this will be the last thing we do today. So we have f of x minus L is less than epsilon whenever 0 is less than x minus c is less than delta. So remember, this is the general equation. What does f of x represent? F of x represent the limit of the function. So this whole thing is the function. So it tells us f of x plus g of x is equal to L plus m. Because this is what we're looking for. And these are the limits. So that goes in place of that, and this goes in place of that. Oops, what's right there? So that becomes, I could move things, let me first get rid of the parentheses. Minus L minus m is less than epsilon. I could change these around. F of x minus L plus g of x minus m. Again, now we have another property from algebra. The property from algebra is this. If we have the absolute value of x plus y, what can we do with that? We can split them up. Absolute value of x plus absolute value of y. So that's what we have here. We have this equation plus this equation. So we have f of x minus L plus g of x minus m is just less than epsilon. Since we have two of them, can they equal epsilon? If in order to equal epsilon, what has to be true? That this one has to be less than epsilon over 2, and then this one, g of x minus m, has to be less than epsilon over 2, because the sum of these has to be less than epsilon. Epsilon over 2 plus epsilon over 2 is what? Epsilon. So when I split these up, I have to take those with respect to x over 2. Then what am I looking for here? Prove that. Yeah, so what we have here, we have this in these two parts. So we have epsilon over 2 plus epsilon over 2 is equal to epsilon, which proves that. Which that was just the pain in the butt one. It's just, you don't have to prove proofs anymore. Should we do the next section or stop here? Because so far, whenever we're talking about limits, we always look at them from both sides. The next section deals with one-sided limits. When would you see one-sided limits? Remember, the function has to be defined on an interval. What if we had a semicircle? Does the limit exist at any point on this curve? Well, yeah. Because at this point here, negative x, I get that one. That's within the domain and the range. This one here, same thing. I could look at the limit from both sides. But what happens at the end points? Can we take a limit at -2? We can from this side because each one of these are approaching it, but we can't do it from that side. Same thing here. We can do the limit as it approaches 2 from the left, but this side doesn't exist. That's what the next part's all about. What happens when our function automatically cuts off half of it, which we can't use anymore? Or the square root of a function. Does the limit exist at every point? How about at this point? Does the limit exist? We can approach it from this side. It's getting closer and closer and closer to 0, but we can't do anything from the left. That's what the next part, we'll do that next time. We'll talk about one-sided limits next time. But so far, we're looking at large enough functions where that they are continuous, which means they can be approached from both sides. Now we're going to look at restrictions on the domain.